Right now, as you watch this video, you're traveling through time at exactly 1 second per second. That seems obvious, right? But here's what will blow your mind. You're also traveling through space at over 600 million miles per hour, hurtling through the cosmos as Earth spins, orbits the sun, and races through our galaxy. Yet you feel perfectly still. What if I told you that the chair you're sitting in right now is actually moving through a four-dimensional fabric that most people can't even imagine exists? And that gravity, the force you think is pulling you down toward Earth, isn't actually a force at all, but rather space and time themselves bending and warping around you like a cosmic trampoline. This isn't science fiction. This is the reality you live in every single day, and most people have no idea. The device you're watching this on right now, whether it's your phone or computer, depends on understanding this hidden reality to function properly. GPS satellites orbiting above us have to account for the fact that time literally runs differently up there than it does down here. Without correcting for this bizarre effect, your navigation would be off by miles within hours. The particle accelerators that led to medical breakthroughs like PET scans and cancer treatments work because scientists learned to manipulate this four-dimensional fabric. Even the way we understand black holes, the birth of the universe, and the possibility of time travel all comes down to one revolutionary insight that changed everything we thought we knew about reality for over 200 years. The greatest minds in science believed that space and time were completely separate things. Space was like an infinite, unchanging stage where the cosmic drama played out. Time was like a universal clock ticking away the same for everyone, everywhere in the universe. It made perfect sense. You could measure distances with rulers and time with clocks. These measurements would be the same whether you were standing still or moving. Isaac Newton built his entire theory of the universe on this foundation. And it worked brilliantly for predicting planetary motion, designing machines, and understanding the physical world around us. But by the late 1800s, cracks began to appear in this neat and tidy picture. Scientists studying light discovered something disturbing. No matter how fast they moved toward or away from a beam of light, they always measured its speed as exactly the same value. This was like saying that if you're in a car driving toward an oncoming vehicle, both vehicles somehow maintain the exact same relative speed whether you're racing toward each other or driving in the same direction. It made no sense according to everything science thought it knew about motion and speed. Then came Albert Einstein, a young patent clerk working in Switzerland, who dared to take this impossible observation seriously. In 1905, he published a paper that didn't just challenge Newton's ideas, it completely shattered our understanding of reality itself. Einstein realized that space and time weren't separate, fixed stages for the universe's events. Instead, they were intimately connected, woven together into a single dynamic fabric that could stretch, compress, and bend. He showed us that time isn't universal. It actually runs differently for different observers depending on how fast they're moving or how strong the gravitational field around them is. This revelation didn't just change physics textbooks. It changed everything. Suddenly, the universe became a far stranger and more wonderful place than anyone had imagined. Past, present, and future weren't fixed universal concepts, but relative experiences that depended on your point of view. The speed of light wasn't just another measurement, it became the ultimate speed limit of the universe. The cosmic constant that holds the very structure of reality together. Mass and energy became interchangeable through the most famous equation in history. And gravity transformed from a mysterious force into the curvature of spacetime itself. With massive objects like stars and planets creating cosmic dents that smaller objects roll along like marbles on a warped surface. Over the next 2 hours, we're going to take you on a journey through one of the most mind-bending concepts in all of science. We'll start with the intuitive world of everyday experience and gradually build up to ideas that will challenge everything you think you know about the nature of reality. You don't need advanced mathematics or a physics degree to understand these concepts, just curiosity, and an open mind willing to accept that the universe is far more amazing than it appears. We'll use simple demonstrations, thought experiments, and real-world examples to show you how space and time weave together into the fabric of space-time, and why this understanding isn't just fascinating intellectual curiosity, but the foundation for technologies you use every day and discoveries that continue to reshape our understanding of existence itself by the end of our exploration. You'll never look at a simple clock the same way again. You'll understand why the GPS in your car needs to account for Einstein's theories to work properly, how scientists detected ripples in spacetime itself using laser detectors, and why the question of whether space and time are the same thing opens up possibilities as exotic as time travel and as fundamental as understanding how the universe began. This is the story of how humanity discovered that reality itself is far stranger and more beautiful than we ever dared to imagine. And it all starts with a simple question that turns out to have the most extraordinary answer. The classical view, separate space and time. Imagine you're sitting in a vast theater watching the greatest show ever performed, the entire universe. In this theater, the stage is enormous, stretching infinitely in all directions. It's perfectly flat, completely unchanging, and provides the backdrop for every cosmic event you can imagine. Stars are born and die on this stage, planets orbit, galaxies collide, and life emerges and evolves. But the stage itself, it remains exactly the same, unmoved and unaffected by the drama playing out upon it. This stage is what Isaac Newton called absolute space, the fixed arena where all physical events occur. Now, imagine that this cosmic theater has the most precise clock ever built, ticking away with perfect regularity. This clock doesn't just keep time for the theater, it keeps time for the entire universe. Whether you're sitting in the front row, standing at the back, or somehow floating above the action, this clock ticks at exactly the same rate for everyone, everywhere. A second on this universal clock is a second for every observer, no matter where they are or how fast they're moving. This is what Newton called absolute time, the universal rhythm that governs all change and motion in the cosmos. For over 2 centuries, this picture of reality worked beautifully. It matched our everyday experience perfectly. When you walk across a room, you move through space, while time continues its steady march forward. When you throw a ball, it travels through the fixed space around you, while the universal clock marks the duration of its flight. Space provided the where, time provided the when, and they seemed as separate and distinct as length and color, or hot and cold. Newton's laws of motion, built on this foundation, could predict the movements of planets with stunning accuracy, explain the behavior of pendulums and projectiles, and provide the mathematical framework for the Industrial Revolution. Think about how intuitive this seems. Right now, you have a clear sense of where you are, your location in space, and when you are, this moment in time. You can point to objects and say they're here or there, measuring distances with rulers or steps. You can discuss events in terms of before, now, and later, measuring durations with clocks and calendars. Space and time feel completely independent. You can move through space without affecting the flow of time. And time passes, whether you're moving or standing perfectly still. In Newton's universe, simultaneity was absolute if 2 events happened at the same moment according to one observer. They happened at the same moment for everyone in the universe. But as the 19th century progressed, scientists began studying something that would eventually topple this comfortable worldview: light. Michael Faraday and James Clerk Maxwell discovered that light was an electromagnetic wave, rippling through space like waves on a pond. These waves traveled at an incredible speed, about 186,000 miles per second. But here's where things got strange. According to Maxwell's equations, light always traveled at this speed. Not sometimes, not approximately, but always. Exactly this speed. This created a puzzling problem. In Newton's universe, if you're in a car driving toward an oncoming vehicle, you add your speeds together to find how fast you're approaching each other. If both cars are going 60 miles per hour, they approach each other at 120 miles per hour. Similarly, if you're driving in the same direction as another car, you subtract speeds if you're going 70 and catching up to a car going 60. Your relative speed is 10 miles per hour. This is basic common sense, confirmed by everyday experience. But light didn't behave this way. Scientists realized that if you measured the speed of light while racing toward its source, you still got exactly the same answer, minus 186,000 miles per second. If you measured it while moving away from the source, you still got the same speed. Even more bizarrely, if you were somehow moving alongside a beam of light at nearly the speed of light itself, you would still measure its speed relative to you as exactly 186,000 miles per second. This was like saying that no matter how fast you drive toward or away from another car, that car always approaches or recedes at exactly the same speed relative to you. Two American physicists, Albert Michelson and Edward Morley, decided to test this strange behavior directly. They reasoned that if light travels through space at a fixed speed, then Earth's motion through space should affect how fast light appears to travel in different directions. Picture yourself swimming in a river. If you swim upstream, the current slows you down. But if you swim downstream, it speeds you up. Similarly, if Earth is moving through space, light traveling in the direction of Earth's motion should appear slower, while light traveling opposite to Earth's motion should appear faster. They built an incredibly sensitive instrument called an interferometer, splitting a beam of light and sending it into perpendicular directions before bringing the beams back together. Any difference in the speed of light in different directions would create a detectable interference pattern. Like the way waves from two stones thrown in a pond create a complex pattern where they meet, they expected to detect Earth's motion through absolute space by observing how it affected light speed in different directions. The results shocked the scientific world. No matter which direction they pointed their instrument, no matter what time of day or season they conducted the experiment, they always measured exactly the same speed for light in all directions. There was no evidence that Earth's motion through space affected light speed at all. It was as if the river had no current, or more accurately, as if the swimmer somehow always moved at the same speed relative to the water regardless of which direction they swam. This failed. Experiment sent shockwaves through the physics community. Some scientists proposed that Earth might be dragging a bubble of space along with it, like a ship creating a pocket of calm water as it moves through the ocean. Others suggested that moving objects might physically contract in the direction of motion, shortening the path light had to travel and making it appear to maintain constant speed. These explanations grew increasingly complex and artificial, requiring more and more assumptions about the nature of space, time, and matter. The classical worldview was cracking under the strain of experimental evidence. The beautiful simplicity of Newton's absolute space and time was being challenged by stubborn facts that refused to fit the theory. Light seemed to be telling scientists something fundamental about the nature of reality. But the message was written in a language nobody yet understood. Space and time, which had seemed so obviously separate and independent, were about to be revealed as intimately connected aspects of something far stranger and more wonderful than anyone had imagined. What scientists didn't realize was that they were witnessing the first signs of a revolution that would completely transform our understanding of reality. The strange behavior of light wasn't an anomaly to be explained away. It was a window into the true nature of space, time, and the cosmos itself. The universe was about to become a far more interesting place than Newton ever dreamed. Einstein's revolution, the birth of spacetime in 1905. A 26-year-old patent clerk in Bern, Switzerland, was thinking about light while riding on a streetcar. Albert Einstein had been puzzling over the strange results of the Michelson-Morley experiment and the bizarre behavior of electromagnetic waves. Instead of trying to explain away these anomalies, Einstein did something revolutionary. He took them seriously and followed their implications to their logical conclusion. What he discovered didn't just solve the mystery of light's constant speed. It revealed that our most basic assumptions about space and time were fundamentally wrong. Einstein's breakthrough began with two simple statements that would change everything. First, the laws of physics must be the same for all observers moving at constant velocities relative to each other. This seems reasonable if you're in a smoothly moving train with the windows closed. You can play catch, pour coffee, or conduct any physics experiment exactly as if the train were sitting still. The laws of physics don't change just because you're moving. Second, The speed of light in a vacuum is the same for all observers, regardless of how fast they're moving or in which direction. This was the radical insight. Einstein didn't try to explain why light behaved this way. He simply accepted the experimental evidence and explored what it meant for our understanding of space and time. These two principles led to conclusions so strange that even Einstein initially doubted them. Let's explore the most mind-bending consequence first: time dilation. Imagine you have a friend who builds a special clock using light. This clock consists of two mirrors facing each other with a beam of light bouncing back and forth between them. Each round trip of the light beam marks one tick of the clock. When this light clock is sitting still relative to you, the light travels straight up and down between the mirrors, covering the shortest possible distance. Now imagine your friend takes this light clock on a high-speed journey. From your perspective, as the clock moves past you, something strange happens to the path of the light beam. The light still bounces between the mirrors, but since the entire clock is moving, the light has to travel a diagonal path up and to the side as it chases the top mirror, then down and to the side as it returns to the bottom mirror. This diagonal path is longer than the straight up and down path the light followed when the clock was stationary. But here's the crucial point: the speed of light must be the same in both cases. If the light has to travel a longer distance at the same speed, it must take more time to complete each round trip. This means the moving clock ticks more slowly than the stationary one. Time itself is running slower for your traveling friend. This isn't just a peculiarity of light clocks. All time runs slower when moving at high speeds. Your friend's biological processes, chemical reactions, radioactive decay, and every other time-dependent process would slow down by exactly the same amount. From your friend's perspective, everything seems perfectly normal. Their watch ticks normally, they age normally, and all their clocks agree with each other. But compared to your time, everything about their existence has slowed down. The effect becomes more dramatic as speeds approach the speed of light. At 90% of light speed, time runs about half as fast for the moving observer. At 99% of light speed, time runs about 7 times slower. At 99.9% of light speed, time crawls at about 1/20th its normal rate. This leads to the famous twin paradox. If one twin travels to a distant star at near light speed while the other stays on Earth, the traveling twin will return younger than their Earth-bound sibling. This isn't just theoretical speculation. We observe time dilation constantly in particle accelerators. Subatomic particles called muons normally decay in about 2/millionths of a second. But when these muons are moving at near-light speeds, they live much longer from our perspective, allowing them to travel much farther before decaying. Without time dilation, cosmic ray muons created in the upper atmosphere would never reach Earth's surface, but they do. In exactly the numbers that Einstein's theory predicts, even more practically. The GPS satellites orbiting Earth experience time dilation, moving at about 8,700 miles per hour in a weaker gravitational field than Earth's surface. Their clocks run slightly faster than clocks on the ground, about 38 microseconds per day faster. This tiny difference would cause GPS errors of several miles within a single day if not corrected. Every time you use GPS navigation, you're relying on Einstein's insights about the nature of time, but time dilation is just the beginning. Einstein's theory also predicts that space itself contracts in the direction of motion. From your perspective, objects moving at high speeds become shorter in the direction they're traveling. A spacecraft flying past you at 90% of light speed would appear to be compressed to about half its normal length, as if someone had squeezed it in a cosmic vice. Again, the crew of the spacecraft wouldn't notice anything unusual. Their rulers would be contracted by the same amount, so all their measurements would seem normal to them. These effects reveal something profound about the nature of reality. The rate at which time passes and the length of objects in space aren't fixed, absolute quantities. They depend on your frame of reference, your state of motion relative to what you're observing. There's no universal correct measurement of time intervals or spatial distances. Two observers moving relative to each other will disagree about when events happen and how much space separates objects, and both will be equally correct from their own perspective. This relativity leads to another startling conclusion: simultaneity is relative. Events that happen at the same time, according to one observer, may not be simultaneous, according to another observer moving relative to the first. Imagine two lightning bolts striking the ends of a moving train simultaneously, according to an observer standing on the platform. To a passenger on the train, who is moving toward one lightning bolt and away from the other, the lightning bolts won't appear simultaneous. The bolt ahead of the train will seem to happen first, followed by the bolt behind the train. This shatters our intuitive notion of now across space. There's no universal present moment that encompasses the entire universe. Your now includes events happening right here on Earth. But it's meaningless to ask what's happening right now on a planet orbiting a distant star. Different observers will disagree about which distant events are happening now, and all will be equally correct. To help visualize these concepts, physicists developed spacetime diagrams where time is plotted on the vertical axis and space on the horizontal axis. In these diagrams, the path of any object through spacetime appears as a line called a world line. Stationary objects have vertical world lines. Moving objects have tilted world lines, and light travels along diagonal lines at a fixed 45-degree angle. These diagrams reveal that space and time are intimately connected. You can't discuss the motion of objects without considering both their spatial path and their temporal duration as aspects of a single spacetime trajectory. Einstein's special relativity revealed that space and time aren't separate entities, but aspects of a unified, four-dimensional fabric called spacetime. Just as an object's orientation affects how much of its length you see when viewed from different angles, an object's motion through spacetime affects how much space and how much time different observers measure. The total spacetime interval between events remains constant, but different observers divide this interval differently between spatial distance and temporal duration. This was just the beginning of Einstein's revolution. Special relativity dealt with objects moving at constant velocities, but what about acceleration and gravity? Einstein's next insight would be even more radical, revealing that gravity itself is nothing more than the curvature of spacetime. The stage was set for an even more mind-bending transformation of our understanding of reality. The unity of space and time. 10 years after publishing Special Relativity, Einstein was grappling with a profound question that would lead to his greatest triumph. Special relativity worked beautifully for objects moving at constant speeds, but it couldn't handle acceleration or gravity. Newton's law of universal gravitation seemed to require instantaneous action at a distance. If the sun suddenly vanished, Earth would immediately fly off in a straight line, even though the light from the sun's disappearance wouldn't reach us for 8 minutes. This violated relativity's prohibition against anything traveling faster than light, including gravitational effects. Einstein's solution began with a deceptively simple thought experiment. Imagine you're in a windowless elevator in deep space, far from any gravitational fields. If someone attaches a rocket to your elevator and accelerates it upward at exactly 9.8 meters per second squared, the same rate that objects fall on Earth, what would you experience inside? You'd feel pressed against the floor with exactly the same sensation as standing on Earth's surface. If you dropped a ball, it would appear to fall to the floor just as it would in Earth's gravity. Every experiment you could perform inside the elevator would give identical results whether you were accelerating in space or sitting stationary in a gravitational field. This led Einstein to a startling realization. There's no way to distinguish between the effects of gravity and acceleration. They're not just similar. They're literally the same thing viewed from different perspectives. This equivalence principle became the foundation for Einstein's general theory of relativity, and it led to the most beautiful and mind-bending description of gravity ever conceived. If gravity and acceleration are equivalent, Einstein reasoned, then gravity can't be a force in the traditional sense. Instead, it must be a manifestation of the geometry of spacetime itself. Massive objects don't pull on other objects through mysterious forces acting at a distance. Instead, they warp and curve the fabric of space-time, creating valleys and hills and the four-dimensional landscape of reality. Objects moving through this curved space-time follow the straightest possible paths, which appear curved from our three-dimensional perspective. To visualize this, imagine space-time as a stretched rubber sheet. If you place a bowling ball in the center, it creates a depression that warps the entire surface. Now, if you roll a marble across the sheet, it won't travel in a straight line. It will curve around the depression created by the bowling ball, potentially even orbiting around it. The marble isn't being pulled by the bowling ball through some mysterious force. It's simply following the straightest possible path through the curved geometry of the surface. This is exactly what happens in our universe, but in 4 dimensions instead of 2. The sun's enormous mass creates a curved depression in space-time, and Earth follows the straightest possible path through this curved region, which appears to us as an elliptical orbit. Earth isn't being pulled toward the sun by a gravitational force. It's moving freely through curved spacetime, following what physicists call a geodesic, the four-dimensional equivalent of a straight line. This revolutionary picture explains gravity as geometry, but it reveals something even more profound about the relationship between space and time. Mass and energy don't just curve space, they curve space-time as a unified entity. The presence of matter affects both the spatial geometry and the rate at which time flows. Near massive objects, time runs slower, space contracts, the normal rules of geometry break down. Consider what happens near a black hole, where space-time curvature becomes extreme. As you approach the event horizon, the point of no return, time dilation becomes so severe that time nearly stops relative to distant observers. Someone watching you fall into a black hole would see you slow down and freeze at the horizon, your image growing dimmer and redder, but never quite disappearing. Meanwhile, from your perspective, you would pass through the horizon normally, but you would see the entire future history of the universe flash by in the region behind you. The curvature of space-time also affects the behavior of light. Light always follows the straightest possible path through space-time. When space-time is curved, these paths appear curved from our perspective. This effect, called gravitational lensing, allows astronomers to observe galaxies that would otherwise be hidden behind massive objects. The gravity of an intervening galaxy bends the light from a more distant galaxy around it, acting like a cosmic magnifying glass. We've even photographed perfect rings of light called Einstein rings, where a distant galaxy is perfectly aligned behind a massive foreground object, creating a circular image as the light is bent around all sides of the gravitational lens, perhaps the most dramatic confirmation of spacetime. Curvature came in 2015, when scientists directly detected gravitational waves, ripples in spacetime itself. When 2 black holes spiral into each other and merge, they create disturbances that propagate outward through spacetime at the speed of light, alternately stretching and compressing space and time as they pass. The LIGO detectors, with arms 4 kilometers long, can detect changes in length smaller than 1/10,000th, the width of a proton as these waves wash over Earth. These gravitational wave detections prove that space-time is not just a mathematical abstraction, it's a real, physical entity that can vibrate and carry energy. When you listen to the audio recordings of gravitational waves, you're literally hearing the sound of space-time itself being shaken by cosmic collisions. Billions of years ago and trillions of miles away, the unity of space and time becomes even more apparent when we consider how motion through space-time works. Everything in the universe, including you, is constantly moving through space-time at the speed of light. But this motion is divided between movement through space and movement through time. When you're sitting still, all of your motion through space-time is directed along the time dimension. You're moving through time at the maximum rate of 1 second per second. When you move through space, some of your motion through space-time gets redirected from the time dimension to the space dimensions, causing time to pass more slowly for you. This is why nothing can exceed the speed of light through space. It would require more than 100% of your motion through space-time, leaving negative motion through time, which is impossible. The speed of light isn't really about light. It's about the fundamental structure of space-time itself. It's the maximum rate at which cause and effect can propagate. The universal speed limit that prevents paradoxes and maintains the logical consistency of reality. This unified spacetime also reveals why Einstein's famous equation E=mc works. Mass and energy are equivalent because they're both measures of how much an object curves spacetime. A massive object at rest curves spacetime in one way, while pure energy like light curves it differently, but both contribute to the total curvature. This equivalence allows the nuclear reactions in the sun to convert a tiny amount of mass into enormous amounts of energy. Powering our solar system for billions of years, the implications extend to our understanding of cosmology. If space-time can be curved by matter and energy, then the entire universe must have a geometry determined by its total contents. This geometry could be flat like an infinite plane, closed like the surface of a sphere, or open like a saddle shape. Current observations suggest our universe is remarkably close to flat on the largest scales. But even tiny deviations from flatness would have profound implications for the ultimate fate of the cosmos. Einstein's general relativity revealed that space and time are not separate background stages for physical events, they're dynamic, flexible aspects of a unified space-time fabric that participates actively in the phenomena it contains. Matter tells space-time how to curve, and curved space-time tells matter how to move. This elegant feedback loop explains not just gravity, but the expansion of the universe, the behavior of black holes, the bending of light, and the fundamental connection between space, time, matter, and energy. The universe revealed by Einstein is far stranger and more beautiful than Newton ever imagined. A cosmos where space and time dance together in perfect unity, where geometry becomes physics, and where the very fabric of reality responds dynamically to the matter and energy it contains. Modern understanding and future frontiers, the story of space-time didn't end with Einstein. In the century since general relativity was published, scientists have pushed the boundaries of our understanding far beyond what even Einstein imagined possible. Today's physicists peer into black holes, detect cosmic collisions from billions of years ago, grapple with mysteries that challenge our most fundamental assumptions about reality itself. The question of whether space and time are truly the same thing has evolved into even deeper questions about the nature of existence itself. One of the most stunning confirmations of Einstein's spacetime came on September 14, 2015, when two massive detectors in Louisiana and Washington simultaneously recorded a signal that had traveled 1.3 billion years to reach. For the first time in human history, we directly detected gravitational waves, actual ripples in the fabric of spacetime itself. The signal lasted only a fifth of a second, but it told an incredible story. Two black holes, each about 30 times more massive than our sun, had been spiraling around each other for millions of years, gradually losing energy by radiating gravitational waves. In their final moments, they accelerated to half the speed of light before merging into a single, more massive black hole. The collision was so violent that it converted 3 times the mass of our sun directly into gravitational wave energy, causing space-time throughout the universe to ring like a struck bell. When these waves reached Earth, they stretched and compressed our planet by less than 1/10,000th the width of a proton, a change so tiny that it would be like detecting a difference of less than the thickness of a human hair in the distance to the nearest star. Yet our instruments were sensitive enough to not only detect this impossibly small distortion, but to reconstruct the entire story of the collision from the wave pattern. Since that first detection, we've observed dozens more gravitational wave events, each one providing unprecedented insights into the most extreme environments in the universe. We've detected the collisions of neutron stars, city-sized objects, so dense that a teaspoon of their material would weigh as much as Mount Everest. These collisions forge heavy elements like gold and platinum, seeding the universe with the materials that make up our jewelry, electronics, and even our own bodies. In a very real sense, gravitational wave astronomy has shown us that we are made of stardust forged in cosmic collisions that warped space-time itself. But gravitational waves have revealed something even more profound about the nature of spacetime. They prove that spacetime isn't just a mathematical description. It's a physical medium that can store and transport energy. When you drop a stone in a pond, the waves that spread outward carry energy away from the impact point. Similarly, when massive objects accelerate, they create waves that carry energy away through spacetime itself. This means spacetime has physical properties, almost like an invisible four-dimensional fluid that fills the universe. This discovery has opened entirely new ways of studying the cosmos. While light can be absorbed or scattered by matter between distant objects and us, gravitational waves pass through everything virtually unimpeded. They provide a clear view of events that would be completely invisible to traditional astronomy. We can now hear the universe in ways that complement what we see with our eyes and telescopes, creating a richer understanding of cosmic phenomena. Yet even as we celebrate these triumphs, modern physics faces profound puzzles that challenge our understanding of spacetime itself. Perhaps the most mysterious is the discovery that 95% of the universe consists of substances we've never directly detected: dark matter and dark energy. Dark matter appears to provide the gravitational scaffolding that holds galaxies together, while dark energy seems to be accelerating the expansion of the universe itself. Both interact gravitationally with spacetime, affecting its curvature and evolution. Yet they remain completely invisible to every instrument we've built, except gravitational detectors. Dark energy, in particular, presents a stunning mystery. Observations of distant supernova revealed that the expansion of the universe isn't slowing down as we expected from gravitational attraction. It's speeding up. Something is stretching spacetime itself at an accelerating rate, overcoming the gravitational attraction of all the matter in the universe. We call this mysterious influence dark energy, but we have almost no idea what it actually is. It could be a property of empty space itself, a new field filling the universe, or evidence that our understanding of spacetime breaks down on the largest scales. This ignorance about the universe's primary constituents raises profound questions about the nature of spacetime itself. If we don't understand what's filling and shaping spacetime, how can we claim to understand spacetime? Some physicists wonder whether space and time are truly fundamental aspects of reality, or whether they emerge from something even more basic that we haven't discovered yet. Quantum mechanics adds another layer of mystery to our understanding of spacetime. At the smallest scales, quantum theory describes reality in terms of probabilities and uncertainties that seem completely at odds with the smooth, continuous geometry of Einstein's spacetime. Quantum particles can exist in multiple states simultaneously, tunnel through barriers that should be impenetrable, and exhibit spooky action at a distance that appears to violate relativity's prohibition against faster-than-light communication. The clash between quantum mechanics and general relativity becomes acute when we try to understand extreme environments like the interior of black holes or the first moments after the Big Bang. Both theories make definite predictions about these scenarios, but their predictions contradict each other. General relativity says spacetime curvature becomes infinite at the center of black holes and at the beginning of time, while quantum mechanics suggests that space and time themselves might break down into a foam-like structure at incredibly small scales. String theory represents one attempt to reconcile these contradictions by proposing that the fundamental building blocks of reality aren't particles but tiny, vibrating strings existing in 10 or 11 dimensions. In this view, the 3 dimensions of space and 1 dimension of time that we experience are just a subset of a higher dimensional reality. Spacetime as we know it might be like the surface of a pond, a relatively calm, 2-dimensional interface hiding the complex 3-dimensional dynamics of the water beneath. Other theories suggest that spacetime might be emergent rather than fundamental, just as temperature emerges from the average motion of countless molecules. Spacetime might emerge from the collective behavior of more basic entities that we haven't yet discovered. Some physicists propose that space and time arise from quantum entanglement between these fundamental constituents, while others suggest they emerge from information processing at the deepest levels of reality, These ideas lead to mind-bending possibilities for the future. If we could manipulate space-time directly, we might create shortcuts through space called wormholes, allowing near-instantaneous travel between distant regions of the universe. We might even create closed time-like curves, paths through space-time that loop back to their own past. While these possibilities remain highly speculative, they're not ruled out by current physics, and they represent the kinds of technologies that a sufficiently advanced civilization might eventually develop, looking toward the future. New gravitational wave detectors will probe deeper into cosmic history, potentially detecting the gravitational wave background left over from the Big Bang itself. Space-based detectors will observe waves from sources invisible to ground-based instruments, while next-generation particle accelerators will probe the quantum structure of space-time at ever smaller scales. We're also developing quantum computers that might simulate space-time behavior in ways impossible with classical computers, potentially revealing new insights about the relationship between information, quantum mechanics, and gravity. Perhaps most intriguingly, we're beginning to test whether space-time has fundamental limits on information storage and processing. The holographic principle suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary, implying that our three-dimensional reality might itself be a holographic projection of information stored on a distant surface. If true, this would mean that the distinction between space and time, and indeed the dimensionality of space itself, might be far more fluid than we've ever imagined, as we push the boundaries of our understanding. The question, are space and time the same thing, continues to evolve. We've learned that they're unified in space-time, that this space-time can bend and vibrate, and that it might emerge from something even more fundamental. The answer reveals not just the nature of space and time, but the deepest principles governing reality itself. Each discovery opens new questions, ensuring that our cosmic journey of understanding has only just begun. So are space and time the same thing? After this incredible journey through the fabric of reality, we can finally answer that profound question. Space and time aren't just similar, they're two aspects of a single unified entity called space-time. They're as inseparable as length and width, as intertwined as melody and rhythm in a cosmic symphony. When you move through space, you affect your passage through time. When massive objects warp space, they simultaneously bend time. When gravitational waves ripple across the universe, they stretch and compress both space and time together as one dynamic, living fabric. But the answer goes deeper than mere unity. What we've discovered is that our everyday experience of separate space and time is like seeing only shadows on a cave wall, a limited glimpse of a far richer, more beautiful reality. The true universe is a four-dimensional space-time where past, present, and future coexist, where matter and energy dance with geometry itself, and where the very fabric of existence responds to the cosmic drama playing out within it. We don't just live in space and time, we are expressions of space-time. Temporary patterns in the endless flow of the cosmic river. This understanding has transformed not just our knowledge, but our daily lives in ways most people never realize. Every time you use GPS to navigate to a new restaurant, you're relying on satellites that correct for the different rates time passes at their altitude compared to Earth's surface. When doctors use PET scans to detect cancer, or when scientists smash particles together to understand the fundamental forces of nature, they're applying insights that emerged from understanding the unity of space and time. The device you're watching this on right now contains technologies that simply couldn't exist without Einstein's revolutionary insights about the nature of reality, but perhaps the most profound implication is what this tells us about our place in the cosmos. We're not separate observers looking at a universe that exists independently of us. We're participants in space-time itself, riding the curvature created by the sun, swept along in the galaxy's rotation through the cosmic web, and intimately connected to every other piece of matter and energy that shapes the geometry of existence. The atoms in your body were forged in stellar furnaces, scattered by supernova that warped space-time itself, and eventually assembled into the complex pattern that thinks, feels, and wonders about its own nature. Looking ahead, we stand at the threshold of even greater discoveries. gravitational wave astronomy is still in its infancy, opening new windows into cosmic events we could never observe with light alone. Quantum computers may soon simulate space-time at scales impossible to explore any other way. And somewhere in the intersection of quantum mechanics and general relativity lies a deeper truth about reality that may revolutionize our understanding once again. We might discover that space-time itself emerges from something even more fundamental, or that our three-dimensional space is actually a holographic projection of information stored on distant cosmic boundaries. The question of whether space and time are the same thing has led us to realize that reality is far stranger, more beautiful, and more unified than we ever imagined. But it's also shown us that the universe is comprehensible to minds like ours, that through careful observation, clever experiments, and bold thinking, we can uncover the deepest secrets of existence itself. Every answer reveals new questions. Every discovery opens new frontiers. And every generation builds on the insights of those who came before. This is the gift that science offers humanity, not just knowledge, but wonder. Not just answers, but better questions. Not just facts, but a sense of our profound connection to the cosmos that created us. The unity of space and time reminds us that we're not isolated beings struggling alone in an indifferent universe. We're expressions of the universe coming to understand itself. Temporary arrangements of matter and energy that have somehow learned to contemplate the very fabric of reality from which we emerge as you go about your day tomorrow. Remember that you're traveling through space-time at the speed of light, following geodesics carved by the mass of the Earth, participating in the cosmic dance that's been unfolding for nearly 14 billion years. The clock on your wall isn't just marking the passage of time. It's measuring your journey through the fourth dimension of reality. The room around you isn't just empty space waiting to be filled, it's part of the dynamic, flexible fabric that connects you to every star galaxy and black hole in the observable universe. If this exploration of space-time has ignited your curiosity about the cosmos, hit that subscribe button and ring the notification bell so you never miss our deep dives into the mysteries of existence. Share this video with anyone who's ever looked up at the stars and wondered about their place in the universe. Because understanding space-time isn't just about physics. It's about recognizing the profound beauty and unity that underlies all of reality. In the comments below, tell us what aspect of space-time amazed you most. Did the reality of time dilation blow your mind? Were you stunned by the idea that gravity is just curved space-time? Or are you excited about the possibility of detecting gravitational waves from the Big Bang itself? We love hearing how these cosmic concepts resonate with your own sense of wonder about the universe, and if you're hungry for more mind-bending physics, check out our video on black holes and the information paradox, where we explore what happens to information that falls into regions of space-time so curved that not even light can escape, or dive into our series on quantum mechanics, where we investigate how the smallest scales of reality challenge our understanding of space, time, and causality itself. The journey to understand space-time has taken us from Newton's absolute space and time through Einstein's revolutionary insights to today's cutting-edge research into the quantum nature of reality itself. But this journey isn't ending, it's just beginning. Every new gravitational wave detection, every advance in quantum computing, and every theoretical breakthrough brings us closer to understanding the deepest nature of existence. Thank you for joining us on this incredible voyage through the fabric of reality. Keep looking up, keep wondering, and keep asking the big questions about the universe we call home. Because in a cosmos where space and time are unified, where matter and geometry dance together, and where consciousness somehow emerges from the interplay of quantum fields and curved space-time, the greatest discoveries are always just one insight away. Until next time. Remember, you're not just in the universe. You are the universe, experiencing itself through the miraculous arrangement of matter and energy that thinks, dreams, and contemplates the very space-time from which it emerged. And that might be the most amazing discovery of all.